Hi, my name is Joylene Shio, and this is my Lab 4 video report on oscillations in a spring mass system. In this lab, I analyzed the motion of a mass swinging in an arc while also oscillating vertically on a spring. My goal was to compare the observed versus predicted motion of a spring mass system. The objectives of this lab is again to compare the observed and predicted motions of the system, and then graphically represent these changes in energy for the computational model. So some fundamentals for this lab was Newton's second law, velocity and position update formula, the energy principle, and then transitional kinetic energy, spring potential energy, gravitational potential energy, and then the time period of oscillation. Some key physics concepts was the system, the earth, the spring, and the attached mass. The surroundings were none, and since the surroundings were none, the change in energy equals 0. Now looking at in the computational model, we set the initial conditions with simple things like the radius of the sphere being 0.03, the color being yellow, etc. And then the main code then lead us to the results, which in this is just a screenshot of the results, which will have a ball oscillating on a spring mass system and rotating. So for the energy graphs, which is plotted, the kinetic energy, the gravitational potential energy, and the spring potential energy, as well as the total energy. As expected, the change in energy remains approximately 0 throughout the simulation, which confirms that the energy principle is satisfied. We also saw that total energy, or the gravitational potential energy and the spring potential energy oscillate in opposites patterns, while K spikes between them. Similarly, with the position graph, for the observation and computational, both have sources of error in the position and energy graphs. Now, when you're looking at further questions, we can ask, is the energy principle satisfied? As looking at the previous graphs, because the total energy sums to 0, the energy principle is satisfied. When we look at the oscillation period, we estimate it for 4 oscillations. And then there's a distance between oscillation and oscillation period directly affects the calculation of K. So when we look at what does this mean, the main thing is looking at the computational versus the actual model. Well, computational model shows that how energy is conserved in a single system without any outside factors. When we look at a real-life model, we realize that there can be difference in energies due to outside factors that are not accounted for. Thank you.